Everyone in this almost last session of the second day of the Global EV Charging Test webinar on best practices EV charging and power quality. So yesterday we had a nice session focusing on best practices for EV charging, and today we have nice presentations on the subject of power quality. The last session will be by me. It will be after this one at 3 o'clock. You can still register for that one. So I would be glad to see you all over there as well. And also afterwards, all sessions will be shown at our YouTube channel, ElaadNL. Also, please subscribe so that you can receive notifications of new videos that are uploaded to the channel. So this session will be hosted by me. Thijs will be collecting the questions. You can ask them using the questions option in the menu. So do not use the chat option, use the questions drop-down menu to ask all questions. And afterwards, I will ask them to Jil. Finally, this event has been made possible by the Progresses project. It's a project supported by Horizon 2020, focusing on improving the efficiency and grid integration of the next generation energy supply for electric vehicles. So it's a nice project focusing on this topic. So then we move on to this presentation. Jil Sutaria will be presenting. She completed a Master of Technology in Power Electronics, Machines and Drives from University in India. And at the moment, she is working on a Ph.D. degree at the Luleå University of Technology in Skellefteå, Sweden. And our main focus is on supraharmonic emissions in large installations like data centers. And the main research interests include power quality, power electronic design, and electromagnetic compatibility. And this presentation will be about a nice effect, or not nice effect, an interesting effect of supraharmonics that can be there in the practice, namely on the operation of residual current devices. So really looking forward to this presentation, and I would say, Jil, the floor is yours.
Yeah, thank you. I'll just get the thing started. Yeah, am I sharing the right screen now?
Yes, it's fine. Thank you.
Yeah. Thank you, Thijs and Tim and Elaad for giving me this opportunity to present our work on RCD. And yeah, so a few words before I start on about myself and the project. So like Tim said, I'm a PhD student. I've been working as a PhD student for 3 years now at Luleå Technical University, which is located in Skellefteå, Sweden, which is very north of Sweden. And so there's lots of snow, almost 7 months any year. And last year we were approached by Energiforsk and Swedish Energy Agency to work on RCDs, that is residual current devices, because a lot of solar power is being added to the grid. And then there were concerns among the Swedish Energy Agency and everyone that how it will impact the RCDs or the safety of people. So we started working on this project. I, along with my colleagues Angela and Nasir, under the supervision of Matt Bolin and Sarah Ronberry, work under this project. And so it has been like 6 months or more than 6 months now that we have been working on this project. So today I'll be presenting some conclusions or results we obtained in these 6 months. I hope they are interesting for everyone. Today I'll be talking about RCDs basically, and then some characteristics of leakage currents. I have worked a bit with the propagation of leakage current, so some characteristics of leakage current. Then on the work that we have done in RCD, some results, and then concluding remarks. So basically, what is this residual current device? So residual current device is basically used in low voltage networks for protection of people from electric shock. And also it's like when there is a fault, and if it's an earth fault, the current doesn't return through neutral and it would return through the protective earth. And if you are by chance touching the live conductor, you will feel the shock. An RCD should be able to detect that and should be able to trip the circuit. So it is used for protecting people from electric shock. Another use of RCD is also for protection against fire hazards. In industrial networks, in industrial places where you have dust and oil. So if there is an insulation failure in those cases, a current as low as 300 milliamps can also lead to fire. So in RCDs are also used for protection against fire hazards. But what are the basic problems with RCDs? So there are two problems that have been seen, or why was there concern for RCDs and their failure? So there are two failure problems that can occur. One is blinding, that is that RCD fails to trip during fault, which is very severe, because if there is a fault condition and RCD doesn't see it and it will not trip, then it can cause, and if someone is touching a live part, then the person will surely face shock. Another is nuisance tripping, which means the RCD trips unnecessarily. I mean, even when there is no fault, it trips. So that is another problem with RCD. What are the probable causes that can occur? So a lot of work has been done for recognizing some of the reasons why these two can happen, and it mainly deals with the waveform distortion that we see. And I have categorized them like according to the frequency range, like DC component. Basically, DC component, DC presence of DC in the leakage current can cause blinding of RCDs. So because they get saturation, we'll see the schematic of RCD in the next slide. So I'll get there. But other than that, quasi-DC, which is like a low frequency AC, which is between 1 to 4 hertz. The term quasi-DC, when we tried to search for, we could get quasi-DC for the magnetic field of the Earth, which was around 4 hertz. And so we mentioned quasi-DC between 1 to 4 hertz. Harmonics, of course, is very much known up till 2 kilohertz. And then you have supraharmonics, which is 2 to 150 kilohertz, which we have seen a lot of sessions in these 2 days. And then we have components above 150 kilohertz, which is conducted emission. So what is an RCD and how does it function, and how can these waveform distortions affect an RCD, and where do these waveform distortions come from? So these are quite a lot of questions that can occur, but first let's start with how does it function. So RCD is a simple device which has mainly two parts. One is an summing current transformer, which is here, and the other one is a relay, electromechanical relay with a permanent magnet. So under normal conditions, when the three-phase current returns through the neutral, the summation of the current is equal to 0. Hence, there is no magnetic field present, and the current in the secondary coil, IS, is equal to 0. So the RCD doesn't do anything. In case of unbalance between the three-phase and neutral, there will be a leakage current. So unbalance can be, there's some unbalance even in steady state condition, and also, of course, if there is an earth fault, there is an unbalance. So there will be some leakage current during fault condition. In either of those conditions, a magnetic field is induced and you have a secondary current IS. This secondary current, when it reaches a predetermined value, opposes the magnetic field which is of this permanent magnet, and this armature which is connected to the yoke is pulled by the spring and the RCD closes. So basically the current has to basically generate enough force so as to oppose the magnetic field of this permanent magnet. So standards define how much should be this value of the tripping current. So according to standards, the value of this tripping current should be anything between 0.5 times the rated current of rated current of the RCD to the rated current of the RCD. So this is a simple definition of RCD. And when I said that DC currents often lead to blinding of RCDs, it is because the RCD has mainly a CT, and it's a current transformer which can get saturated due to the presence of DC currents. But in today's presentation, I'll not be talking about pure DC current, although we have worked with pure DC current as well, but I'll be presenting more with the what we found in our results with quasi-DC, supraharmonics, and harmonics. So how do they affect the operation of RCD? Because it's not very straightforward like DC. I mean, I don't know if it really generates a saturation or how does it impact. So that is the reason why we did the study. So there are different types of waveform distortion. There are different types of RCDs also, and the oldest one is a type AC RCD, which is just meant for pure AC. So it just detects pure AC current in the leakage current and trips based on that. And it has several ratings: 6, 10 milliampere, 30 milliampere, 100 milliampere, 300, and 500 milliampere. Out of which till 30 milliampere the RCDs are used for human protection, and above 30 milliampere the RCDs are used for fire hazard protection. So type A RCD is used for pure AC as well as pulsating DC, and it can also take up till 6 milliampere of smooth DC. Type B RCD, which is one of the most important RCDs which we should be using these days, is also used for AC, pure DC, pulsating DC, and even high frequency currents up till 1 kilohertz. And type F RCDs, which are especially for high frequency currents, pulsating DC, and pure AC currents. So these are the 4 types of RCDs. But what are the reasons or what are the devices which cause this kind of distortion? So those devices we have been talking about a lot, I think, in these 2 days, of what causes it. But some of them are are shown here. So a lot of devices which have power electronic converters generate these kind of distortions, namely harmonics and supraharmonics, or even low frequency harmonics. So like in this case, for instance, this is a measurement I did with a computer, CPU of a computer, which had a computer power supply, which was switching at 85 kilohertz. And this is a spectrogram which shows the time versus frequency. So you can see how the supraharmonic varies. So in case of this computer, it is a steady emission at 85 kilohertz, and it is absent for every 0 crossing, and again it is there. This is where we had an electric vehicle, and we have a solar panel in our lab, or inverter in our lab, solar inverter. So we had measured EVs, several EVs, and we had connected them with this solar inverter, and we had done some measurements. So one of the EVs and solar solar inverter, when they were connected together, this is how the supraharmonic emission from EV looks. This time varying emission is from 40 to 50 kilohertz is from the EV, whereas the steady state emission at 16 kilohertz is from PV. So these EV and PV are, like you can see, very strong source of supraharmonic emissions. And also, of course, you have the quasi-DC emission and DC emissions coming from solar inverters, as well as DC, as well as car chargers, EV chargers. And this is the last one is the emission from LED lamps, which are also, because in Sweden all the lamps have been now replaced with LED lamps. So even smaller emission counts. So this also has this kind of frequency variation. So supraharmonics as a whole is not one thing. I mean, it is different types. It can be broadband, it can be narrowband, or it can be just frequency varying in time. So such devices, when connected to grid, can generate these kind of distortions. But how is it normally dealt with? Like, how do we protect the grid against the emissions? So usually all the devices have an EMI filter. The EMI filter is basically not meant to protect against supraharmonics. It has it should stop any frequency greater than 150 kilohertz, that is in the till 30 megahertz, that is in the conducted emission range. But it usually has a corner frequency. The AMI filter usually has a corner frequency around 9 kilohertz. So it also gives it a low impedance path. What this will do is you will have supraharmonic emissions in the PE currents. So this is next what we did was we did the PE current measurements for several devices, and some of them I have presented here, like the solar inverter that we were talking about, which is there in the lab. This is how the PE current, this is how the PE current looks for the solar inverter. And I tried to calculate a ratio of, in the PE current or in the leakage current, how much is the percentage of supraharmonic emission from the solar inverter, and it is around 90%. So because the PE current in steady state condition is not supposed to have the 50 hertz component, because the system is usually balanced. So whatever comes in through the phase should return through neutral. So but the EMI filters in these devices provide a low impedance path, and hence the supraharmonics end up in the leakage current. So they are around 90% of the as compared to the fundamental. Similarly, this is from the EV that we saw. So for that EV, it has a broadband emission between 45 to 50 kilohertz, and it is varying in time as well. So this emission, if I take a ratio of this emission with respect to the fundamental, it is around 242%. That is around 200%. So we can rather see, like, that it is mostly the high frequency emission, which is what PE current is composed of. And in this case, we use the microwave, and we did measurement in microwave, and we saw that there is a DC component even in the time domain waveform that we can see. So this DC component was around 40% of the fundamental component. So yeah, so this is how the leakage current looks, and this is why there was a concern about how the leakage currents or the waveform composition of leakage current impacts the RCDs. Also, this is something about how the leakage current changes with the connection of the devices, or and how they pass through the EMI filters. So some of the leakage current basically changes with the state of the device, whether the device is turned on or off. In the sense, if the device is off, it is not generating leakage current. But then what happens is, if there is any other device which is connected to the same phase as your device, and even if your device is in turned off mode, the emissions from that device can propagate through the to the leakage to the protective earth through the other device. So basically they propagate amongst themselves. So it changes according to the state of a device. And also if some device which doesn't have its own PE connection, such as LED lamps, which are usually very small, which usually have very small emission in terms of supraharmonic emission, but even that emission, if it ends up in the leakage current, then it is going to increase the leakage current value. So here is an example of some measurements we did in our lab. This is the measurement of where I had computers, LED lamps, and a microwave connected to the same phase. And then the computers there are 3 computers, and you can see the emission of this computer, which is 69, 70, and 71 kilohertz. And the emission of computer changed according to the state of microwave. This is the measurement done at one of the computer terminals, one of the peak terminals of computer. And so here, when the microwave is turned off, the emission is higher, that is the black one. And when the microwave is turned on, the emission damps a bit. And also here you can see this emission is from the LED lamps, because we separately tested and we know the range in which the emission happens. So this is the emission from LED lamps. So this way you have supraharmonics coming on the towards protective earth. So keeping all this in mind, we had to decide how do we approach this project. And then we decided something like this, that we first map the characteristics of different RCDs. So we have around 13 RCDs, and then we decided separate distortion cases. We tested 4 hertz as in for quasi-dc. We are among harmonic harmonics, we have tested with several harmonic, but I think the third harmonic is the most effective one. So I'll be presenting some results on third harmonic as well. And then we did a test with supraharmonic, some frequencies, and also some combination of supraharmonics and harmonics and a fundamental component. This was the test characteristics that we have used, or distortion cases that we have used to test. And then we use a setup that is defined by IEC 61008-1 and IEC 62423. So this is for type A and AC, and this is for type B and F. But the test setup is quite similar, because in IEC 62423, they refer to using the same test setup as 61008-1. And then how did we assess the behavior of RCDs? That is based on the magnitude of 50 Hertz component in the tripping current, and whether according to that magnitude, if the RCD is blinding or if it is an unwanted tripping. So this is the test setup that is recommended in the IEC 61008, the schematic, which is shown. So in this schematic, basically we used a programmable voltage source and a waveform generator, and we had an amplifier. So with the help of a waveform generator and amplifier, we used a voltage source here to supply the RCDs. And as you can see, the input through the RCD is through both phase and neutral, but the output is only through the phase through a variable resistor and back to neutral. So the output of the RCD sees only one out, means that the RCD would see an unbalance between phase and neutral, and it would trip. And you have to change the value of this resistance, and then change the value of the leakage current that is flowing through the RCD, and we can see where it trips. So on the right hand side is a small is how it looked in the lab, is how the setup, how it looked in the lab. We had RCDs mounted in a proper box, and then the measurement, and then the variable resistor. Okay, so for according to the standard 61000-8, every test has to be performed 5 times, and an average value of the result has to be considered. So keeping that in mind, we first built a base case with only 50 Hertz component, and we had total 13 RCDs of different types, like type A, AC, and type B, and different ratings, 30 milliampere and 300 milliampere. So we have I will be presenting results like that for 30 milliampere and 300 milliampere RCDs separately. And the base case, what you see is this is the average value of the after 5 tests. This is the average value at which the RCD was tripping, but we created a tolerance value among these 5 values. How was the variance? And according to the variance, we decided plus or minus this much. If the tripping current of any RCD falls within this range of plus or minus, then it is considered to be in the range that we define. Or this is how we define whether the RCD is false tripping or whether it is blinding. So we compare our results with this base case. So next, we have some results which I would present with supraharmonics. So these are the waveforms. This is some of the waveforms that we used for supraharmonics. And what we did is we have made 3 test cases where a supraharmonic of 11.5 kilohertz is 50% of that of fundamental, 100% of that of fundamental, and 200% of that of fundamental. And you can see the increase in the supraharmonics on the time domain waveform as well. And on the right hand side is the frequency spectrum, where you can see the 50%, 100%, and 200% of supraharmonics. When we tested all these 13 RCDs with these 3 waveforms, and so we get these kind of this result. On the left hand side is the RMS value of the tripping current that we got for different cases, and there is a comparison with the base case in this case. So if you see the RMS value, the RCD, they are all rated 30 milliampere, which means they should trip somewhere between 15 milliamperes and 30 milliamperes. But all of these RCDs still 100% are below 30 milliamperes, but the one with 200% is above 30 milliamperes. So if you see this, you would feel that the RCDs in case of 200 milliamperes fail to trip, because they should be tripping somewhere below 30 milliamperes. But this is just the RMS value, including the RMS value of 11.5 kilohertz or supraharmonics. Whereas on the right hand side, for the same base case and 100% of supraharmonics, 11.5 kilohertz, if you see, this is just the 50 hertz component that is there, and the 50 hertz, all the 50 hertz component is within the range for all the RCDs. So then it is not false tripping. They tripped accordingly. So in the standard, they mention RMS value, but when we had meetings with several RCD manufacturers, they all consider that 50 hertz component only has to be considered in the tripping current. So we actually, there is a need to clarify which frequency components are to be considered, in the leakage current, or what should be the constitution of the leakage current that should be counted as 15 milliamperes, whether it should be the overall RMS value or whether it should be just the 50 hertz component. But anyway, going further, we considered 50 hertz component because that is what all the RCD manufacturers told us. So for now, we will be comparing the results with 50 hertz component. But this is a clarification, I think, that is needed. So then next what we did is we had 11.5 kilohertz. Same we compared with 34.5 kilohertz also. So now we have a case where we have 100% of 11.5 kilohertz and 80% of 34.5 kilohertz. And you can see for 50 hertz tripping current, in case of 34.5 kilohertz for all type A RCDs, higher tripping current is required for fundamental. So from this we concluded that the tripping first thing is due to the 50 hertz component, because the 50 hertz component in all the three cases, although is different, is not that different. So mainly the tripping in this RCD is caused by the 50 hertz component. And when we tested purely with supraharmonics, that is no 50 hertz component, the RCDs did not trip, or if they tripped, it required really high currents, which would, I guess, which is quite not possible to have in the leakage current, but it requires very high current for pure supraharmonics. Then next is 34.5 kilohertz component. So it is a frequency dependent phenomena, because in case of 34.5 kilohertz, you require higher fundamental component to trip the same RCD. So if you go higher in the frequency range, maybe the amount of 50 hertz component required increases. So here the concern is, as long as the 50 hertz component is below 30 milliampere, it is fine. But if the 50 hertz component increases above 30 milliampere so as to trip, then it will be a fail to trip scenario, and that is a dangerous situation. Next, supraharmonics and harmonics. This is with 150 hertz component. So we have a 50 hertz component, 150 hertz component, and supraharmonics, because third harmonic is the most common component which is there. And here there is a lot of research that has been carried out with the angle of the harmonic with respect to the fundamental. So we have tested two cases where we have a 50 hertz component 180 degrees phase shifted with respect to fundamental, and 150 hertz component 0 degrees phase shifted with respect to fundamental, and there and 11.5 kilohertz component is superimposed on that, and all the three of them are in equal magnitude, so they are like 100%. So if you see, on the left hand side for 300 milliampere RCDs, this is the result for the 50 hertz tripping current that is present. So you can see that 150 hertz, the RCDs should trip from 150 hertz and above. But for RCDs AA here, if in case of 150 hertz and 0 degrees, and the RCDs trip below 150 hertz component, and this is false tripping of the RCDs. If we just consider 50 hertz component, then it is a false trip for the RCDs. And similarly for type AC RCDs, here you have for 150 hertz and 180 degrees, 0 even below 150 hertz, 150 milliampere. So this is also a false trip condition. And also overall, yeah, if we saw that for RCDs with 0 degrees, 150 hertz and 0 degrees, they tripped with a lower fundamental current as compared to the base case. So yeah, this is the second one where we have 30 milliampere RCDs, 150 hertz and 11.5 kilohertz, and these are all type A RCDs. And in type A RCDs, particularly, we saw that for these two RCDs, let's say that 150 hertz 0 degrees, they were tripping at lower than 15 milliampere. On the left, this one is where you have 150 hertz and fundamental comparison. So we just try to trip with 150 hertz component, and all the RCDs, of course, tripped, and they have tripped with much higher current because this is a pure tone 150 hertz component. But above this frequency, like for 250 hertz, 350 hertz, some RCDs tripped, but some RCDs did not. We have tested up to 1000 hertz, and some of the RCDs tripped and some did not trip. But for 150 hertz, all of the RCDs tripped. So for type A RCDs. So from this we concluded that if you have 150 hertz component, then it contributes to the tripping of the RCD. It increases the chances that for the RCDs to trip. And yeah, next is quasi-dc. Quasi-dc component, 4 hertz, we tested with 4 hertz for quasi-dc. And in case of type A RCDs, this is where pure quasi-dc 4 hertz components, and this is what was fundamental. But with pure tones, it requires really high currents, like 400 amps, 400 milliamps, 600 milliamps for it to trip. Although it trips, it's very high. And with a combination of currents where the 4 hertz component was 48% of fundamental, all the RCDs tripped at a lower value. So they all tripped like with lower fundamental current is required for them to trip. So even 4 hertz basically helps for type A RCDs to trip. Then next is 50 hertz tripping for 300 milliampere. For 300 milliamperes, we have different types of RCDs: A, AC, B, and BSI. Type A RCDs do not trip for 4 hertz component, and they are not even meant to trip. And that is one of the major problems. If you have type A RCDs, they do not detect DC or even quasi-DC components. So they did not trip. Type AC RCDs tripped, but they required, of course, higher current. And in this case also, it is a different behavior. Type B RCDs also tripped with 4 hertz component, and in fact they required slightly lower fundamental current in type B RCDs. So but a general conclusion we could not reach for just type B RCDs, because we have only two type B RCDs. Yeah, so considering all this, what is the risk of human hazard at higher frequencies? So for this, I came across a very old paper by Dan Ciel, and he at that time had done measurements with people in 1943, and there's a curve of let go current at different frequencies at which people can let go without of their own, without any external help, if they are clutching a live conductor. So we made a comparison of some of the non-tripping currents. I mean, a current at which no RCD was tripping, minimum current at which no RCD was tripping. We could go keep going higher and they wouldn't trip. So for 4 hertz, let's say it is this green dot, which is already above 100 milliampere, and for 150 milliampere, 150 hertz, it's this. Then at 11.5 kilohertz, it is this. So all of these non-tripping current values are way above the let go current. So if you have pure tones of these frequencies, you will not be able to easily let go a live conductor. Basically, what is the sensation that you feel due to the high frequencies? They said it is mostly internal heating that is felt, and the muscular reaction becomes sluggish. And same effects were reported for frequencies near DC in that paper. I have added a reference for that paper if anyone wants to read it. Yeah, with this, I would come to some of the concluding remarks. So a basic conclusion then we came up with is that a clarification is needed in the definition of the tripping current, or what should be the frequency component, what should be the composition of the tripping current. Some standards already have a composite leakage current with which the RCD should be tested, but it is only till 1000 hertz and not above that. So and there's no mention of quasi-dc currents in the leakage currents. So maybe that also can be included. So a clarification is needed there, and also whether the RMS value should be considered or only the 50 hertz component should be considered when judging whether the RCD was fail trip or whether it blinded. So that kind of conclusion. Then second is for 4 hertz component and supraharmonic components, in presence of these two waveform distortions, a higher 50 hertz component was needed for the RCDs to trip. At least RCDs of type A type A already showed this kind of a behavior. And fail to trip situations were seen when you have pure tones of higher than 150 hertz and 4 hertz for in some cases. Okay, but overall we did not see like a very dangerous situation with this much percentage of supraharmonics. I mean, we have gone up till 200%, but if you have a really high percentage of supraharmonics and if it requires a lot more 50 hertz component to trip, then it could become a dangerous situation. But till now we have not come across that kind of dangerous situation. These are the references. This work we have it has been accepted in CIRED. So it will be a paper which is presented in CIRED, and the other references are, it is one of my papers, and the other paper was with the lead co-currents. Yeah, thank you. Yeah, I hope so I finished in time. Yeah.
Yes, thank you so much for your nice presentation. And again, I think some very important conclusions that also for this part, there is still some work to be done on regulation. The standards really need to adapt to also take into account these kind of things, because you see more supraharmonics and quasi-DC in practice as well. So that leads me to the first question I had. It's about the quasi-DC components. How do they exist in practice? What is the source of this kind of components?
Yeah, I think it is mainly with the solar inverters and with the EV chargers that you like you have a PWM, like the variable PWM, maybe that, or you have some kind of a interaction between two devices which generates this frequency modulation, and you have a low frequency component coming in that case. So wherever you have two converters together, or else you already have like this DC component in case of solar inverters. So those are the equipments where you can have quasi-DC components, basically.
Okay, and I know for installations with PV or EV, you need to have some DC detection, the 6 milliamps detection. Will this also be able to see the quasi-DC component?
Yeah, well, I don't think because it is very difficult to judge how strong your CTs or the sensor is. If it has 1 hertz resolution or not, then otherwise it will club it into DC and might be able to see some part as DC probably, because it's a very it will appear, it's 0.25 seconds, so it will appear on a large time scale. So probably you need a larger time scale to see it as well. So I don't know, if you have a smaller window, probably you cannot see the 200 millisecond window. You will not be able to see the 4 hertz component.
Yeah,
we had
indeed.
to even choose like 2 second. Yeah, then we could see it.
Yeah. Another question is from Mahendra Shilikuri. What is the emission level of the supraharmonics in your study? And I think he means in the phase currents, what the emission of the supraharmonic was like.
No, so in the phase currents, this is according to the test setup. We are already passing it in the phase current, and we used 100% of fundamental and 200% of fundamental. I mean, the phase current, since it doesn't return through the neutral, it would behave as a leakage current. So I guess it is 100% and 200% of the fundamental in my test case. We did other test cases also where we had two sources, and in one case the current goes back from one phase to neutral, and the other phase is open. like I guess it is one of your papers as well. In that case as well, we use the 100% to 100% as the test cases. Yeah,
Okay,
but that
that's
one
clear.
I've not presented here. Yeah.
And if you would have equipment like an EV, you did also measure the leakage currents of those devices?
Yeah, that is what I had shown in the presentation. The leakage current was the one that I had presented. So in the leakage current, you have supraharmonics, which is like 90% in case of solar inverter, and was 200% or 250% in case of EV. That is the leakage current. Because in phase current, your fundamental is quite high. So of course, you cannot have like 200% of fundamental in phase current. But in leakage current, due to EMI filters, the supraharmonics propagate through to the PE, and hence you have higher amount of supraharmonics there because the fundamental is very low, of course, because almost everything goes back to neutral.
Yeah.
So yeah, in that case only you will have this. Yeah, those
That's
were
clear.
some measurements we did in our lab here.
Okay. Another question is maybe already partly answered in your presentation from Amir Broshi. What is the human body impedance like in higher frequencies? Is it higher or lower than at 50 Hertz? Because this will affect the 30 milliamp value.
Well, yeah, I haven't measured the human body impedance or how it would be, but the impacts that was stated was something like this. I think it is we are more resistant to the higher frequencies because we feel the heating, but we don't feel the shock that we would feel at 50 Hertz component. So I guess that is how I should take it. Yeah.
Yeah, I think I remember I wrote it in my paper that there's a standard from IEC. I'm not sure which one it was, that gives some frequency factor with which you multiply the 30 milliamp value for higher frequencies. So then for increasing frequency, you have an increased leakage current as well. So this will conclude that the impedance will also be higher for higher frequencies. So there will be less current flowing to the body. But
yeah, but that curve is up till 1000 Hertz. We don't have anything higher than that curve. Yeah.
Indeed. So that's a good question. What will happen with higher components?
Yeah, what would happen? Because I don't know if it goes like after a while lower again. No. Yeah, we need a reference for that.
Another question also from Amir Broshi. Did you check parallel installation of type A RCDs?
No, we have not tested two parallel type RCDs, but it's a good suggestion. Probably we should do it. Like we used two RCDs, but it was never like testing them together, or how would they trip. But I guess maybe we'll do it. We tested them individually. We have not tested both of them together. No.
Yeah. Okay, then one final question for myself. Do you have any recommendations based on your results, maybe for manufacturers of the RCDs or from installation owners? Should they worry? Should they change something? What would you say?
Yeah, I mean, I think it is mostly for the standards that we recommend that we should include, because of the presence of so many power electronic based devices like solar inverters and even EV chargers. We should have some tests for the leakage current for RCDs even at higher frequencies. There should be some test cases, standardized test cases, as well as what should be considered. Whether only the RMS current should be considered or 50 Hertz component, because the idea is that the current transformer in the relay or in the RCD basically would act as a filter for a lot higher frequencies. But then we see in our studies that although it acts as a filter, the 50 Hertz component that is required increases when you have the high frequency component. So where is that limit? That how much should be allowed. So I guess there should be some standard setup for that. I think so, and that would be my recommendation. And for users of EV, type B RCDs as recommended are good. They should be used instead of just type A RCDs.
Yeah,
I think.
Okay. Well, thank you for your nice presentation and for the discussion we had. I'm going to close the session. the next one in 50 minutes will be me presenting about my research. So I hope to see you there as well.
Yeah.
So thank you, and
bye-bye.
Bye-bye.
Bye.